the mean or the expected value of a continuous random variable. Now, we've been looking at, prior to this, discrete random variables. So with the discrete random variable, you may well remember the expression for the mean or the expected value. So discrete random variable, we saw that the mean had the symbol mu, or sometimes it was written expectation of x. Might have been written in this form. So it's basically a sigma px type thing. So sum of all the probabilities times their value. Okay. Maybe it was written a bit like that, perhaps. Something like that, or equivalent. Okay, so that was for a discrete random variable, which we've seen. So that leads us naturally, plus if we fuse together, I suppose, what we've learned about probability density functions, okay, we can come up with an expression for the mean for a continuous random variable. So from negative infinity to infinity, x times f of x, the given function. Okay, so for a continuous function, we can find it that way, or you might see it as just with slightly different notation, something perhaps like this. Very, very similar. Okay, just P denoting probability, right? Now, if you have one of those functions, if let's use f of x, right? Some function f, and its probability is 0 for all values of x outside of the interval CD, where C and D are real numbers. So that means they're not an element of the interval CD. Then the expected value, or the mean for this variable x just is the integral from C to D of x times f of x. That means you know how we've seen so far some parts where the value of the function is 0 otherwise outside of a certain interval. Alright, that contributes nothing to the mean or the expected value because it has a value of 0 through those intervals. We'll look at an example and I'll show you what I mean. Find the expected value of the random variable x which has a probability density function with this rule in our familiar piecewise scenarios. So what we do basically, now in general this is what we're after, but specifically here, have a look, these intervals here, the function has a value of 0, that contributes nothing. So this is where the action is, folks, right there, 0 to 2. So what we really want for a useful integral for us is x times 0.5x. Okay, so the f of x in the useful relevant part, okay, is 0.5x. So we go x times that f of x. So it's x times 0.5x in this particular case. And that's pretty easy to integrate. Okay, that's 0.5x squared. And it's also this. Taking the integral, the definite integral. So that's x cubed over 3. Alright, so we've done our integration and we apply our limits of integration from 2 to 0. So it'll be 0.5 or a half times 8 over 3 minus 0. So we've got a half times 8 over 3, which is 4 over 3. So the expected value, or the mean, is 4/3. Now a variation on this is what's called the composition of the random variable x. So it's not just the mean of x, okay, it's the mean of a function of x. So it's like a function of some sort of variable, okay. So this will be important also for when we soon will look at the variance of a continuous random variable. That's coming up in a video very soon. So how do we do that? Well, basically that's our notation, and we take the integral from negative infinity to infinity of whatever g of x is times f of x. So it's g of x by f of x. Okay, and we're going to see how that works. So that occurs a lot, and an example immediately below shows an example of that. So let x be a random variable with the probability density function as such. Now that's the same as what we saw before, that one, but we've got to find different things. The expected value of x squared and the expected value of e to the x. So do part A first. Alright, so this one here is basically we're talking from 0 to 2, like we saw in the previous example, for the reasons we stated before, and it's the g of x is x squared. Okay, we write it in terms of the lowercase variable x, of course, and so we've got x squared times 0.5x. And we can manipulate that prior to integrating. We could say 0.5 outside of the integral 0 to 2 of x cubed. Okay, and that's not too tough. It's not that bad. So, and doing our integration, we've got 16 over 4. So we've got half of 16 over 4. Which is 8 over 4, which is 2. Last part of the video, what about if the function g of x is e to the x? Okay, so this one will be from 0 to 2 of e to the x times 0.5x dx. Okay, now that, again, whoops, that's an equal sign, 0.5 times the integral. Now, that's an interesting one to integrate, isn't it? It depends what guise you're watching this video in. If you are doing a subject that knows, like specialist maths in Queensland, you can use, one thing that you could use there is integration by parts. But if you are doing, say, mathematical methods in Queensland, as an example of a subject, you may need to use integration by recognition, which, not as good, but yeah, if you think about it, you'll get it out. I have earlier videos on both of those topics, so go check them out. It's a bit like this is recognition, by the way. It's a bit like trial and error type integration, and it's only really suitable for reasonably simple stuff. So I'm assuming that we're doing this with recognition. Integration by parts is a lot more certain way to go. But if you took the derivative of this function I've got there in pink, e to the x times x minus e to the x, you'll actually get this, and then that simplifies down to that. So it's a little bit guess and check, a little bit trial and error, but you can do it in a sensible way. So that's basically what we're looking at here. So we get that, and subbing in our values, we've got 2, so that'd be e squared, or 2e squared minus e squared minus, let's put some brackets there, little brackets, squeeze them in. Okay, so we got first term will be 0 when we sub in 0 because x is 0, and the second term will be e to the 0, which is 1, so that's 0 minus 1, which is negative 1 there. Okay, so we've got a half. I'm going to change that to a half. 2e squared minus 1e squared is just e squared. Minus negative 1 is plus 1. You could leave it like that, or you could use a decimal approximation like that.